Here is a ball being rolled off a high building with a horizontal speed to begin with. Now what we're going to do is photograph the ball every second, and we're going to put a special filter on the camera which is going to show us the components of the velocity acting on the ball. So for example, when we begin to push the ball off, it's going to have a certain horizontal velocity. Now as 1 second passes, the ball will reach this position, and you now can see that it's got a horizontal velocity which is unchanged, but it's now got a vertical velocity acting downwards. 1 second later after that, you can see that the vertical velocity acting downwards has got bigger, but the horizontal one hasn't got bigger at all, it stayed the same. And just before it hits the ground, you can see the vertical velocity has increased again, and the horizontal one has stayed the same. So what's exactly happening here then? Well, we know that the horizontal velocity remains constant because there's no horizontal force acting on the ball to accelerate it once it's pushed off the table. When it's pushed off the table, the velocity that it has is going to in fact stay the same because there's no acceleration acting horizontally. So the horizontal component, as we say, of the velocity of the ball stays the same. But it's different with the vertical component. The vertical component velocity increases because the force of gravity is accelerating the ball downwards, and the minute the ball leaves the top of that high building, its velocity vertically downwards is going to be zero, but gravity, the acceleration of gravity is not going to act on it, and therefore the velocity of the ball is going to increase downwards as the time goes on. Now the path the ball takes, this horizontal projectile as we call it takes, is a well-known path. It's called a parabola, and you can see it there. One of the most famous parabolas you can get in maths, and yet that's what happens when a ball is rolled off a table. The path of it is a parabola. Now let's take a look at the kind of maths of what's going on here, the figures, and let's imagine we're going to push the ball off a tall tower with a horizontal velocity of 4 meters per second. Now the ball has an initial vertical velocity of 0 because just as it leaves that tall building, it hasn't got any vertical velocity because the acceleration acting on it hasn't had a chance to act. It's like time t equal to 0. Horizontally, it's got a horizontal velocity of 4 meters per second. So how do we actually calculate the vertical velocity at any time in that flight? Now to find the size of the vertical velocity at any time t after it was set in motion, we just use our equation v equals u plus at, where v is the final velocity, u being the initial velocity, and a being acceleration, and t being the time. So v equals u plus at. But because the initial vertical velocity is 0, is coming off the top of the tower, then it can be found just by simply using v equals at. We can just ignore the initial velocity because it's 0. But we'll keep it in to see the calculation. So 1 second later, we have this situation here. The horizontal velocity stays the same, 4 meters per second. But look at the vertical velocity. Acceleration due to gravity is acting on it, and after 1 second, the speed will be v equals u, which is going to be 0, plus 9.8 times 1. So the velocity, the vertical velocity after 1 second, will be 9.8 meters per second. The next second of the journey, once again, the horizontal velocity stays the same because there's no acceleration in the horizontal part. But the vertical velocity has changed, and it's changed since the beginning. We say v equals u plus at. It's been in flight for 2 seconds, so the equation now becomes v equal to 0 plus 9.8 times 2, and we have a new vertical velocity of 19.6 meters per second. And finally, just before it hits the ground, we're going to have the same horizontal velocity, 4 meters per second, but this time the vertical velocity has changed. It's going to be this time 9.8 times 3, add the initial velocity, which is 0. That's going to give us 29.4 meters per second. So there's a picture of what's happening. The horizontal velocity stays the same because it's not accelerating in the horizontal part, but the vertical velocity does because it's accelerating due to the force of gravity, and it accelerates with an acceleration of 9.8 meters per second every second. So every second its velocity is going to increase by 9.8 metres per second. Now, at any time in that flight, I can work out the two components of that ball's velocity. A ball is pushed off a high tower with a horizontal speed of 8 metres per second, said the lady. There is no air resistance. Determine the size of the horizontal and the vertical velocities 1.5 seconds later. Well, I know if it's been pushed off at 8 metres per second that the horizontal velocity will still be 8 metres per second because it's not accelerating. But vertically, it is accelerating due to the force of gravity. So 1.5 seconds later, there you go, first of all, the horizontal velocity remains unchanged. But 1.5 seconds later, we have to use our equation. V equals u plus at. V equals 0, because initially, vertically, it's got no velocity. And it's been going for 1.5 under the influence of acceleration of gravity. And it's going to be 9.8 times 1.5. So at that particular point, it's going to have a downward velocity of 4.7 metres per second. And that's that drawn in there. So there's our two components of that ball's velocity. 8 metres per second horizontally, and 1.5 seconds into the flight, it's now got a downward velocity of 14.7 metres per second. Now, we'd like to know what the resultant velocity is in this situation, and to do that we've got to look closely at the two vectors. The horizontal component vector is 8 metres per second and the vertical component is 14.7 metres per second. Now, to add those two velocity vectors together, you must add them nose to tail. Now, in that particular configuration, they're in tail to tail, so we can't add them together or make a diagram out of them. But what we can do is move the 14.7 metres per second vector over such that its tail is going to touch the nose of the 8 metres per second one. And now what we can do is we can see we've got a start, and we've got the nose, tail, and finally the finish down here. So our resultant vector is going to be that one there. So how do we find the size of that vector? Well, we could do it two ways. We could draw a scale diagram, and that would just mean on a piece of paper drawing 8 metres per second and 14.7 in that configuration and measuring this size here, and then using a protractor to find this angle here. Or we could go ahead and just use trigonometry and Pythagoras. You'd find V by using Pythagoras, and you'd use Pythagoras as follows. You can see we've got a hypotenuse and a right angle triangle, and therefore the maths of it is quite simple. The V squared is going to be 8 squared plus 14.7 squared. And when you do the maths of that, you get V equals 16.7 metres per second. So the resultant velocity of that ball is 16.7 metres per second. But we still got to find the direction which the ball is going in. And we can easily do that by putting in the angle below the horizontal, and that would be that angle there. So we can put in the angle like that and just find what that angle is. And once again, that's a trigonometry work. So we can say that the tan of that angle is the opposite over adjacent. So tan is going to be the opposite side, 14.7, divided by the adjacent, 8 metres per second. And we get an angle of 61 degrees. So to fully describe the velocity of that ball, we would say it has a magnitude of 16.7 metres per second at a direction of 61 degrees below the horizontal, that being the horizontal. So it'll be 61 degrees below that. If I just asked you the speed of the ball, the resultant speed, you would just quote the size of it, 16.7. So here's the ball being rolled off a high table with a horizontal velocity of 4 metres per second, and we want to analyse the motion of that ball's flight. Now, as you can see, there are two different motions acting on that ball at the same time. There's a horizontal motion acting on it, and there's a vertical motion acting on it. And these can be described in terms of the components of the velocity of that ball. A horizontal component, shown in green, and a vertical component of the velocity shown in blue. Now we want to show a graph of those two motions, the horizontal and the vertical. If we take a look at the horizontal graph of the horizontal motion, we can see that the velocity time graph is just a straight line right across the page at 4 meters per second because the velocity is unchanged. So the horizontal graph of the horizontal component of that motion is just a straight line right across with the speed in which the ball was rolled off the table. And you can see it there, horizontal velocity 4 meters per second. So the horizontal velocity is constant at 4 meters per second, and it's a horizontal velocity. It is in fact no acceleration. But the vertical component is going to be different. The graph is going to be different from that. Now, I'll stop the video here and you can draw down what you think the vertical component graph looks like of the velocity, and then you can restart the video and see if you got it right. So on you go, draw it now. Welcome back. Let's see if you got the correct graph. Yes, that's the correct graph there. The vertical component starts with a velocity of 0 downwards, and then as the time goes on, after 1 second, the acceleration of gravity kicks in, and you can see they're going to have an increase in the velocity all the way up due to the acceleration of gravity. And that is the graph of the vertical component of that ball's velocity. So two different graphs there, one showing no acceleration, constant velocity, and the vertical velocity one showing that the graph is accelerating. If you worked out the acceleration of that graph, you would get an acceleration of 9.8 meters per second every second. So that is the vertical velocity is increasing due to the acceleration caused by the force of gravity, and you can see from that graph there that it's a straight line through the origin as the velocity increases due to the acceleration of gravity. Now we can get more information from those two graphs, and it's a very useful piece of information. From the horizontal velocity of the graph, we can work out that distance there between the edge of the cliff and where it lands. That's given a special title called the range. And what's more, in a velocity time graph, if you work out the area of the graph, you've worked out the distance gone. So that area in there, the area of the horizontal velocity time graph, is actually equal to the horizontal distance travelled by the projectile. That's given a special name called the range R. So that distance here can be found from the area of the horizontal velocity time graph. Now what about the height the ball fell down? What about the distance the ball fell down by? Well, we can guess that it's going to be the area of the vertical velocity graph. And indeed it is. If we work out the area of the vertical velocity graph, then we get the height the ball fell from. So there's two important pieces of information we can get just by looking at the horizontal velocity graph and the vertical velocity graph. The area of the horizontal velocity up to the time the ball lands is what we call the range, the distance from where it started along the ground to where it landed. The heights in which the ball fell can be found from the vertical velocity graph, working out the area underneath the vertical velocity graph.